Okay, so as usual, you're gonna need to do the odds. I'm gonna do the evens. For homework, you're gonna want to do 1, 3, 5, 7. I'm gonna do A for you, but you're gonna do B. 9, and that's all. I'm about to do 2, 4, 6, 8, 10, and we'll see if I have time. Maybe I'll do 11 as well. I think 11's a good one, but I don't want to assign it to you. Okay, so let's start with number 2. Make sure you're reading along with me. An important part of this process is taking information from the problem. Suppose that water waves have a wavelength of 2.4 meters. So let's get that down. Remember, the symbol for wavelength is lambda. So the distance between two peaks is 2.4 meters. And a period of 1.6 seconds. So period we want to represent with an uppercase T. So 1.6 seconds, that's the amount of seconds per cycle. So for every wave that passes by, 1.6 goes by. So we want to know the velocity of these waves. How quickly are these moving past a given point in this period of time if they are spread out by this distance between peaks? So we don't have an expression that relates these three variables. So what we want to do first is let's write down an equation that we know we do have that solves for velocity. Velocity equals frequency multiplied by wavelength. And we also have an equation that relates frequency to period. So we know that frequency is equal to the inverse of period. You should have seen that in the lab yesterday. This is an equation that will be on the board. This is an equation that will be on the board. You're going to have to combine these two. So we're going to want to rewrite the equation for velocity. But instead of writing frequency, we're going to write what frequency is equal to, which we've just shown is 1 divided by the period. So then we'll multiply that by the wavelength. All I've done is replace this f here with 1 over t because they are equivalent. So now we have everything we need. We can start plugging our numbers in. The velocity of this wave is going to be equal to 1, I should have put the units over here. Technically it's seconds per cycle, but 1.6, oh, let me back that up. 1 divided by 1.6 seconds multiplied by 2.4 meters. And then let me just let you know this is number 2 right here. Okay, so when I multiply this through, I'm just going to turn it in one big fraction. 2.4 meters times 1 equals 2.4 meters divided by 1.6 seconds. So our units come out to be the units for velocity, which is what we want. 2.4 divided by 1.6 is equal to 1.5 meters per second. So that's the velocity of this water wave. So that one was a lot harder than both 1 and 3, but you will have to do something very similar to this on your quiz. You're going to have to combine this formula with this formula. All right, so that was number 2. Make sure you do 1 and 3. I'm going to move on to number 4. Okay, number 4 says, a wave on a rope is shown in the diagram. What is the wavelength of this wave? So let me try to draw this out. So this wave has 3 peaks, So there's 2, 3. Across the center of this wave is the resting line where this medium would be if it wasn't excited. And it shows the distance from the almost to the end of 6 meters, from here to here. 6 meters. So this asks what the wavelength is. So what we can do is count how many total waves are in this distance. So one full wave is just how long it takes to go through a cycle. So this is 1 cycle here, 2 cycles here. So this is 2 waves, which means this wavelength is half of this distance, and half of 6 is going to give us the wavelength. So the wavelength equals 6 meters divided by 2, or 3 meters. So this is number 4 we're doing here. So I believe this is A. So let's move on to B. If the frequency of this wave is 2 hertz, what is the wave speed? So let's write down what we're given. Frequency of 2 hertz. And we want to know what is the speed of this wave. Oops. So we do have an equation to relate these. Speed is equal to frequency times wavelength. So we can just plug these numbers right into this equation. It's going to be 2 hertz. Now instead of writing hertz, I'm going to write what a hertz actually is. It's the inverse of seconds. And we're going to multiply that by 3 meters. 2 times 3 equals 6. Meters times 1 is meters divided by seconds. So we have a speed of 6 meters per second. So I think this one's pretty easy. This is just like 1 and 3. The main thing is here knowing what one full wave is. So I like to think of a wave as looking at it like an S turned sideways. Like this is one wave right there. There's many different ways to define it, but this I think is the best way. So this is 1, 2 waves in the 6 meter distance, giving us a 3 meter wavelength. Okay, so let's move on to number 6. Number 6 says, suppose that a guitar string has a length of 0.8 meters. So let's get that down. All right. And a mass of 0.12 kilograms. And if there's a tension exerted on it of 135 newtons. I think before when I introduced tension, I used uppercase T. That was a mistake of me because we have period represented by uppercase T. So for tension, since it's a force, we want to use F, and then to show that it's a tension force, we'll give it the subscript of uppercase T. So the tension exerted on the string is 135 newtons. So acting in opposite directions, there's a tensional force of 135 newtons. So just think about it like from each end, forces are pulling in opposite directions. All right, so what is the mass per unit length of this string? So this is something I introduced last week. Mass per unit length, sometimes known as length density, is this funny Greek letter mu here, and it's the quotient of the mass divided by the length. So all we have to do, plug our mass in, 0.12 kilograms, and divide that by our length of 0.8 meters. So 0.12 kilograms divided by 0.8 meters gives us 0.15 kilograms per meter. So for every 1 meter of distance, there's 0.15 kilograms. That's mass length density. So this was A. So B asks us to find the velocity or the speed of this wave. So there's a new equation that I need to show you. Now we already saw from our lab last week that velocity is directly proportional to the force of tension. Remember we stretched our string out, or our slinky out, the speed of the wave was faster. And we saw that the velocity of the wave was inversely proportional to the mass length density. When we decreased our mass length density, our speed got faster. So we're going to combine these two equations, or these two expressions, to get a new equation to solve for the speed of a wave. The only thing that's different that I need to throw in here is this radical symbol. We need to take the square root of this quotient. So the velocity of a wave is equal to the square root of the tensional forces acting on it divided by the mass length ratio. So sometimes we're going to have to actually plug this formula into this denominator, and then you're working with a fraction within a fraction, so it gets a little bit messy with the algebra, but I'll make sure that on Monday you see an example of how to work with that before your quiz. Alright, so we have the tensional force, 135 newtons. We just solved for the mass per length ratio, or the length density of 0.15 kilograms per meter. So, I'll spare you more messy handwriting. I could show you how these units cancel out to give you velocity. Feel free to try it out if you remember what newtons are, kilograms times meters divided by seconds squared. But this is just too sloppy to show you here. So the velocity of this wave comes out to be 30 meters per second. Make sure that before you do this square root, you divide 135 by 0.15 and then take the square root. Otherwise, you're not going to get the correct answer. This is the last thing that you do when you are using your calculator. Okay, that takes care of number 6. Don't forget to do 5 and 7. Now, I'm going to do 7a for you. 7b is pretty easy. 7a, there's something kind of new that I need to introduce to you. A string with a length of 0.8 meters is fixed at both ends. So let me get that down. This is 7a. You need to do b. The length of this string is equal to 0.8 meters. So if I have a string attached at this end to this end, it has a distance or a length through space of 0.8 meters. So A says, what is the longest possible wavelength for the traveling waves that can interfere to form a standing wave? So we saw this on our simulation, traveling waves creating to make standing waves. But if I was to excite this, the longest possible wave that could be made is just like what it looked like when you were doing a half wave of your slinky. So it would go from resting like this to being excited like this. So this is the longest wavelength, but this is only half a wave. So to keep this going, to make a full wave, or to figure out what the full wavelength would be, we would have to finish that wave. So this is that S I was talking about. So here you have half of a wave. So 7a says, what is the full wavelength? Well, the wavelength is going to be twice the length. So all we have to do is plug in our length. Well, I use the lowercase l. You get what I'm saying though, hopefully. 2 times 0.8 meters, and that gives me a full length of 1.6, or a full wavelength of 1.6 meters. So if I was to excite this a little further, just like I was saying you could do from your lab with the Slinky, you would decrease the wavelength to this point right here. Alright, so that's 7A. 7B should be easy for you. It's just using this equation. But I think you have to solve for frequency. Yeah, so that's simple algebra for you. Alright, so I'm going to do 8 now. Suppose the string in exercise 7 is plucked so that the 2 nodes along the string, in addition to those that are at either end, what is the wavelength of the interfering waves for this node? I'm actually going to go back to the last page. So we're using the same exact length. So this is number 8. Don't forget to do 7b. So this says 2 nodes along the string in addition to those at either end. So I think what we need to do is just draw the nodes first. Now remember, the nodes are the parts where there's no motion. So I have 2 nodes in addition to the 2 at the end. So this last dot over here lines up with this one, and this first dot over here lines up with this one. So I have these 2 nodes in the center. So I'm going to draw my wave, and I'm going to make sure that it goes at the resting point through these 2 nodes. Alright, so my distance hasn't changed. The length of my wave, or the length of my string, is still 0.8 meters. What has changed is the number of waves in this distance. So I think it's easy if we break this wave into thirds. So here's 1/3 of it, not the wave, break this length into thirds. Here's 1/3, here's 2/3, here's 3/3. So if we want to know what the wavelength of this new standing wave is, we have to look at, out of all of these parts, how much of them make up the whole wave. So here's 1/3 of it, 2/3 of it, 3/3 of it. So if you look at just the first 2/3, that right there gives you your wavelength. So here's one full wave right here. So what that means is our wavelength is going to be equal to 2/3 of the length. So all we have to do is plug in our length into this formula right here. This isn't a formula that you would see in a book or on the board during your test. We just kind of had to figure that out using some logic. So 2 divided by 3 times 0.8, should say meters in there. So 2 times 0.8 is 1.6 divided by 3 gives us about 0.5 repeating 3 meters. Alright, now we can move on to number 10. Number 10 is just like number 9. They're both very easy. They're just different context. It's talking about sound waves, which are longitudinal instead of what we've been talking about so far, transverse waves. So here we go. Number 10. What is the frequency of a sound wave with a wavelength of 0.85 meters? Traveling in room temperature of the air. So at room temperature, sound waves travel at about 340 meters per second. And we are asked to find the frequency. All right, so this is a very simple problem. You're just using this formula and solving for this variable. So if we want to know what frequency is, and right now it's multiplied by wavelength, to get rid of multiplied by, the inverse operation, division. Whatever you do to one side, do it to the other. Wavelengths cancel out. So this implies, that's what that arrow means, is that frequency is equal to the quotient of velocity and wavelength. I'd say 80% of the problems are just using this equation and doing one simple algebraic manipulation. So the velocity we were given, sound travels through the air at about 340 meters per second. And the wavelength of this wave is 0.85 meters. So before I do the arithmetic, look what happens here. My meters cancel out, and I'm left with the units of seconds in the denominator. Now you don't see anything up top, but what you would have left is 1. And your units are going to be 1 over seconds. So 340 divided by 0.85 gives you 400. So I believe this was actually the frequency in the first part of your lab yesterday. 400, 1 over seconds. So you could also write this as 400 seconds to the negative 1th power, or what's most commonly used is the units of hertz. Okay, so that takes care of number 10. I'm going to do 11 for you, but you only have to do 1, 3, 5, 7, and 9. I want to do 11 for you just because it helps explain something that some of you were asking about yesterday during your lab. And it also is just good to get more practice. But right now you've seen everything that you need to in order to do your homework. Okay, so number 11. An organ pipe closed at one end and open at the other has a length of 0.5 meters. So, closed at one end, and shade this in. This is just like the black cap that you put at the end of the boom whacker. So this length right here is 0.5 meters. This is number 11. What is the longest possible wavelength for the interference or interfering sound waves that can form a standing wave in this pipe? So before I show you this one, let me show you if the pipe was open, what it would look like. So this is open on both ends. Same length, just not closed. So if this pipe was open on both ends, it would be a longitudinal wave, but those are really hard to draw. What it would look like is this right here to represent the longitudinal waves. So right here, this is half of a wave. So the full wavelength for the vibration of the air inside of a pipe open at both ends would be twice this distance. So since this is half of a meter, it would be twice that, which is 1 full meter. But for an open pipe, it's a little bit different. What it looks like is you can only get 1/2 of one full wavelength, and 1/2 of 1 is 1/4. So the wavelength for an organ with a closed end, or an organ pipe with a closed end, is going to be 4 times the length. Whereas if this was an open end, it would just be 2 times the length. So all we have to do is plug in the length, 4 times 0.5 meters, and that gives us a wavelength of 2 meters. If I pop the cap off, just like in your boom whacker, or opened up one pipe of the organ, it would be only twice that, which means a much higher frequency. All right, so that is A. For B, what is the frequency associated with the standing wave if the speed of sound is 340? So we're looking for frequency. We know velocity. And we know wavelength. Okay, so I can do the algebra for you. Showed you last problem. Velocity divided by wavelength gives us frequency. The velocity is 340 meters per second. The wavelength is 2 meters. And 340 divided by 2 gives us 170 hertz. So, don't forget your homework. You get graded for doing this classwork, but it's only 5 out of 10 points of your homework. Your homework is to do 1, 3, 5, 7B, and 9. All right, have a good weekend.